So let's start. نجمر طولو قبولو تشاتشو. So now the corrected specific fuel consumption is given, which is the ratio of corrected mass flow, fuel mass flow rate divided by the corrected thrust, and which finally gives us the actual mass flow rate of fuel divided by thrust times the temperature ratio. Radical of temperature ratio. And another is the corrected thrust specific fuel consumption, which is also similar to that of specific fuel consumption, but the application of thrust specific fuel consumption and specific fuel consumption are different. So we can use that both terms in our aircraft performance course in order to find the range and the endurance equation. The Berkut range equation and the Berkut endurance equation needs these parameters for jet aircraft and the propeller-driven aircrafts. For them, it is different. In actual propeller-driven aircraft, we need power, the power. So power is thrust times velocity. And for the jet aircraft, we need only thrust. So that thrust-specific fuel consumption is mainly used for jet aircraft, because in the jet aircraft, our intention is on thrust rather than power. Okay, so in this case, F is our actual thrust produced by the engine, and TSFS is actual thrust-specific fuel consumption, and which is a measure of fuel efficiency. This thrust-specific fuel consumption is, it measures the fuel efficiency of an aircraft. Okay, MF is the actual fuel flow measured in mass per unit time, the amount of fuel consumed, the amount of fuel or the mass of fuel consumed per unit time. So the next topic is about inlet compressor matching. Inlet compressor matching is our main topic here. So inlet compressor matching ensures that the air delivered by the inlet is compatible with the air flow and pressure requirements of the compressor, so that the engine operates stable and efficient under all flight conditions. That is the requirement. So inlet and compressor are the adjacent components. They have to match each other in order to deliver compatible flow. Okay, so why the inlet compressor matching is important? This is because it prevents flow separation and distortion at compressor phase, and it avoids compressor surge and stall. It ensures the required mass flow enters the engine and maintain pressure recovery and overall engine efficiency. And also, it is required because critical during off-design condition. Off-design condition, when I say takeoff condition, climb condition, cruising at high Mach condition. So these are the requirements why we need to match inlet compressor components. So in the analysis of this inlet compressor matching, we have this schematic. We are familiar with this picture in our previous chapters. So we have a far stream conditions, A naught, P naught, T naught, M naught, which ambient condition. And we have inlet condition here. So represented with 1, and the mass flow rate of oxidizer, that oxygen or nitrogen, the ambient air is coming into the inlet with M naught dot. Okay, which enters into that, the compressor section will immediately get that amount, that second 2 section. So the schematic drawing of an inlet coupled to fan or compressor, which is shown in this picture, and on which the fixed area are the inlet lip. A1 is called area at the inlet lip. Again, A2 indicates engine face area. A2 indicates engine face area. And compressor exit area is represented with A3 here, A3. And the variable is the free stream capture area. So here, zero or not indicate that free stream condition, okay, which is simply A naught is given there, which is a strong function of flight condition. So such as that takeoff, climb, cruise, okay. We may establish flight total pressure, temperature, using static values and flight Mach number M naught. So that are the free stream conditions. Again, flight Mach number and total pressure properties in the cycle components must match end of design analysis. Therefore, the physical flow rate through an area A is connected to the actual Mach number, MZ. So look, we have MZ here, MZ2, MZ3, okay? So this actual Mach number that is different from M naught, okay? So local pressure as PT and TT are there, okay? So the expression for the mass flow rate in terms of this variable is M dot, that is the mass flow rate of the gas, which is equal to gamma R, radical of gamma over R times PT divided by radical of T. This is actually, this equation already we represented here. This is already here. It indicates what? MCI. The MCI equation will be repeated here, okay? MCI equation, so this MI indicates MCI, okay? And the engine phase mass flow rate on the engine phase at location 2, because we represented it with I. Now 2 indicates the I there, so this is the engine phase mass flow rate. Again, the inlet mass flow rate is represented with M naught because M, as we observe this picture, the engine inlet is with M naught, mass flow rate of the air only. So that is M naught. And the law of conservation of mass needed that the inflow rate and the outflow rate in the engine to be equal. That is the conservation law. So we can put M2 is equal to M naught. That gives us this equation. And this equation needs some kind of rearrangement, okay? So the M naught conditions are represented with A naught, M naught, T naught, PT naught, and so on. And M2 conditions are represented with A2, MZ2, and so on. So it needs some kind of rearrangement. And once we rearrange it, what we can get is this kind of equation. So equation 12 represents the balance between the inlet condition and the compressor condition. So this equation is completely known for the given Mach number, flight Mach number, M naught, and the left-hand side consists of 3 unknowns. So left-hand side means the one with MZ, pi d is not known. Again, A naught is not known. The free stream capture area A naught is not known. Initial total pressure recovery pi d is not known. And the actual Mach number MZ2 is not known. So 3 unknowns are there. So we have to find some method in order to determine these 3 unknowns, okay? So typical inlet performance map contains inlet recovery variation with flight Mach number, that is pi d. So pi d, which is equal to F of M naught. This pi d is called the total pressure recovery. Okay, so it is already known. It is function of the free stream Mach number. And therefore, the mass and energy balance for the inlet compressor results in two unknowns. A naught and mz naught are not known for the flight Mach number. So the main area of concern here is inlet compressor matching, which is connected with the inlet distortion problem. So the unsteadiness and instability in compressor and fan, which we call it as compressor surge, find the another problem, which is in inlet distortion condition. The third is compressor and combustor matching. Look, these are the neighborhood components. Compressor is there, combustor or combustion chamber is there. So the compressor leads airflow towards to the combustion chamber. So on the combustion chamber, the air from the compressor come into the combustion chamber, and the fuel injector will inject fuel into the combustion chamber. Then heating will take place on that. So they are adjacent components. Therefore, they need to match each other in order to ensure stable and efficient flow. So compressor combustor matching ensures the air delivered by the compressor is suitable for the combustor's requirement, so that the engine operates safely, efficiently, and without flow instability. So what is the importance of compressor combustor matching? One is to prevent compressor flame out or pressure oscillations. That means instability of the pressure. Again, to maintain a required pressure and temperature for turbine entry, and to ensure correct air-fuel ratio, that stoichiometric ratio, F, air-fuel ratio, F, for efficient combustion. And finally, it is important because it is critical for off-design operations like takeoff, climb, cruise, and other conditions. The third is compressor. This is actually that part, compressor combustor matching. So on that, we can see here, this schematic diagram represents the compressor combustor matching with their respective mass flow rates, area, and Mach number. So we have area 3, the exit of compressor area, okay, and it is inlet for the combustion chamber area, inlet for combustion chamber and exit for the compressor. Okay, so in this diagram, what we can see, mass of fuel flow rate is represent mf dot. Mass of air is coming from through the compressor is there. And we have different components, shafts, radial bearings, and other components are there. And the shaft is rotating with omega, which is equal to 2 pi n. Okay. And once the fuel and the oxidizer mix together, what we can obtain from the combustion chamber is m naught dot plus mf dot. That is the hot gas mixture. Okay. So these all things are there, and the shaft, turbine shaft power represented with Q. QT indicates turbine shaft. So these combinations are there here. So the mass flow rate M4 is equal to M3 plus MF. You see M4 here, the mass flow rate of M4 is equal to M naught dot plus MF dot. That is the mass flow rate at the burner exit. Okay. And which we can represent it by 1 plus F. F is the fuel to air ratio, stoichiometric ratio. Okay. Therefore, 1 plus F the whole times M naught of the air, which is equal to 1 plus F times M2 dot. That so this is just mass flow rate balance. So the unknown on the right hand side indicates the 1 plus F condition. So R the fuel to air ratio. So actually, which are known actually. And the actual Mach number MZ2 is not known. And the fuel to air ratio is set by throttle. So we have to set the fuel to fuel to air ratio by throttling the engine. Therefore, we consider the throttle setting as a noun in and of design operation. And we can write this equation in terms of thermodynamic relations. Okay, so this is actually m.4. So we relate pressure total 4, temperature total 4, area 4, Mach number 4. So same equation as previous. As we have seen for different sections, we use that m dot equations. So this is the equation. If we take station 4 as the exit of the first turbine nozzle, then over a wide operating condition, it remains choked. That means M4 is equal to 1. Choked condition means that is the throat condition. So that is Mach is equal to 1. And the combustor exits total pressure, PT4 is equal to the pressure recovery times PT3. So PT3 is pressure total at 0.3. 0.3 means the inlet, the combustor inlet condition. Okay, combustor inlet condition pressure times the pressure recovery gives us the total pressure at exit of the burner or the combustion chamber. Okay, so we have to match these things. So that helps us to calculate PT4 pressure at the exit of the burner is equals to the recovery pressure times pressure recovery time pressure at the inlet of the combustor. Which are also another correction factor, pi c also is there. Again, pi b is there, pi d is there. So these all are the correction factors. So what are these? We are now T naught, T2, T3, and T4. So for T4, we have only pi b. For T2, we have pi b times pi c. Pi c is the compressor. Again, pi d, pi b, pi c. These recovery conditions. Okay, so we multiply these things in order to match all the pressure conditions through inlet, compressor, burner, and so on. So the combustor exit total temperature T4 is a throttle setting dependent and is treated as noun. So we can put that temperature simply. Just we can substitute this result here. Pi b, pi c over radical of T4, T2. Just considering the 2 and 4. So this is actually our final result here. So this equation is a function of actual flow Mach number. Actual flow Mach number MZ2 is here. We have to define that. Again, here it is MZ2, okay, at 0.2. What we are relating this condition with? 0.2. That is compressor inlet condition. Yeah, so it is there. We conclude that for the given compressor, corrected mass flow rate and engine throttle setting, TT4 to T2, and the fuel to oxidizer ratio, we can establish a unique compressor temperature ratio pi c. So pi c is compressor temperature ratio. Okay, so we have this pi c, which is compressor temperature ratio. So the path of steady state engine operation, we have this figure actually. On this figure, we can observe different sections. Pi C, the compressor pressure ratio pi C is there. MC2, the mass flow rate of through the compressor is there. So in this diagram, we can observe the operating line. This is the bold line indicates the operating line or steady state line. And in steady state line, we can see at different section, different conditions. Transient deceleration is represented backward flow here. And the transient acceleration is in the forward flow from node 2 to node 3, we can observe here. So that is transient acceleration. And this line indicates n over radical of theta. N is the RPM of the shaft, and the radical theta, theta the power of 0.5 means radical theta. That means theta the power of 1 over 2. That is temperature ratio. And when we go to these lines, it indicates increasing the throttle. Temperature T4 over T, the temperature T2 indicates the throttle condition. So that condition indicates the increasing condition from bottom to upward. And the above line here, it indicates stall or surge line for the compressor, okay, or for the engine. Okay, this is surge line. And the middle line indicates what? Constant throttle line, okay, constant throttle line. So this is the schematic representation of this condition or this equation. Okay, so that equation 16 can be provided alternatively with different parameters, actually. Just choosing an appropriate value of pi C, the compressor pressure ratio, the actual flow Mach number at the turbine entry, and the throttle condition TT4 to TT2, and the pi B, the pressure recovery. And we can calculate area ratio, area of 4 by area of 2. Area of 4 is the combustion chamber exit area, and area 2 is the throttle entry area. So that ratio can be easily calculated from knowing these parameters. So this area ratio actually, A4 to A2 is constant for the fixed area turbines. So therefore, then we can use the energy balance equation again, which energy balance equation in terms of the enthalpy HT4 to HT3. And also we have the fuel energetic property QR is there, and the efficiency is also there. So using this equation, we can calculate the energy balance across the combustor, which provides the fuel to air ratio. Actually, F here, our F indicates fuel to air ratio, which is enthalpy at 0.4 minus enthalpy at 0.3 divided by QR neta B minus HT4. So this is the fuel energetic properties actually. Assuming that in the throttle condition, we have these parameters, F times QR neta B, the efficiency, divided by T2, which is related with CP at the throat, what we call this, CPT over CPC. So turbine to compressor ratio. Now, here what we are, the specific heat at turbine divided by specific heat at compressor. Actually, they are different because as the gas is heated into maximum temperature, the value of Cp is different. And which is times temperature at 4 over temperature at 2 minus tau C. That tau C is also another ratio. So finally, the compressor power is matched to the shaft power produced by the turbine. That Q is the shaft power there. Okay. So that is what we call the compressor combustor matching condition. The next is combustor turbine matching condition. Combustor turbine matching condition. We are taking them the adjacent sections. So what is that? It ensures that the hot gas leaving the combustor are compatible with the turbine flow and energy requirements, allowing the turbine to extract the required work efficiently and safely. Okay? So heat produced in the combustor and which is flowing through the turbine, so that must be compatible with each other. And why it is important here? It is just to prevent the turbine blades overheating or failure of the turbine blade. Again, to ensure turbine turbine receives correct mass flow and temperature. And the third, to maintain power balance with compressor and other shaft-driven components. Okay. And finally, for the off-design, critical off-design operations. So this combustor turbine matching in the steady combustor turbine interaction, which is dominated by choked turbine nozzle, that is Mach 4 is 1. Mach 4 means the turbine inlet Mach number, which is 1. Turbine cooling requirements, because turbine encounter with hot gas, so that cooling requirements is there. And hot spots in the turbine entry, and also loss of turbine efficiency due to heating, that is cooling is required. So the effect of cooling on the turbine aerodynamics is modeled as some equivalent uncooled turbine operating at lower adiabatic efficiency. So the turbine efficiency neta T is equal to 0.75 up to 0.85. So this is the amount of turbine efficiency. So we can see this figure, actually combustor turbine matching. So this section is just combustor section, and this section is turbine section. Therefore, the hot gas which come out from, actually here we have cooled turbine and uncooled turbine and cooled turbine condition. The first figure represents uncooled turbine. So what happened on that? Look, there is shaft power QT, that is the turbine power, the rotation of turbine which produces shaft power. So shaft is rotating with some RPM, and the turbine shaft, which is W is equal to 2 pi n, is the radial velocity of the turbine. Okay, so we have mass of air entering into the combustion chamber, mass of fuel is injected into combustion chamber, and then A4 is exit area for the combustor. But for the turbine, it is inlet area, right? So once it enter into the turbine, then it goes to A5. So this is totally the turbine area. But in the case of cooled turbine, when a ram of air is coming and to the turbine and cool, because the atmospheric air entering into the combustion chamber is not only for the purpose of burning the fuel, but some of the air goes to cool the hot sections. So the ram of air is coming like this. The bold line which you can see indicates the cooling system. So when it is cooled, the combustion chamber the entry is 1 minus zeta 1 times mass of air, mass flow rate of air is entering to the combustion chamber. Again, within the combustion chamber, you can find 1 minus zeta 1 minus zeta 2, the whole times mass of air, which enter here. And the remaining mass of air, zeta 2 m naught, is cooling the system. That zeta 2 m naught is for the purpose of cooling the, here also zeta 1 m naught cooling the high pressure turbine and high pressure turbine and low pressure turbines are cooled with zeta 1 and zeta 2 efficiency. So this helps cooling. Okay, so the physical condition here we can represent. This figure shows the combustor turbine with part A is showing uncooled turbine and part B is showing cooled turbine. The two epsilon 1 and epsilon 2 are air cooling mass flow fractions. Okay, they are air cooling. Some amount of air is going for the cooling purpose to the turbine in the high pressure turbine and low pressure turbine condition. So that are leveled from the compressor at intermediate pressure point and at compressor exit respectively. So that's what we represent. So we can write the mass flow rate of the compressor at 4. 4 indicates the exit point for the combustor. So which is actual mass flow rate of combustor. This is actually fuel and air mixture now. Times temperature, radical of temperature ratio at 4 divided by the pressure ratio at 4. And MC5 is the compressor exit. No, the turbine exit point, which is the actual flow of 5 or the exit of the turbine. The whole times temperature, radical of temperature ratio at 5 divided by the pressure ratio. So that is what we have. Okay, so therefore, taking the ratio of the two expressions, MC4 over MC5, we have left turbine pressure ratio divided by radical of TT, zeta T. So this zeta T is one unknown parameter here. Okay. So again, we are related for cooled turbine, M4, mass flow rate from 4. Actual mass flow rate from 4 is 1 plus the stoichiometric ratio of the fuel to oxidizer minus epsilon 1 minus epsilon 2 times M naught. M naught is the mass flow rate of air. M5 is 1 plus F. F is the ratio, the fuel to air ratio, the whole times mass flow rate of air. So these are the combustor turbine matching conditions. So when we divide them, what we can get? What we can get is 1 minus epsilon 1 plus epsilon 2 divided by 1 plus F the whole times pi t over radical zeta t. So in this case, the case of cool turbine, temperature 5 is reduced as result of coolant injection in the hot gas. Okay, temperature 5 is reduced than when it is compared with the temperature at the combustion chamber. So impact of cooling the turbine is on turbine pressure ratio is also reduced as turbulent mixing of the coolant injection into the hot gas, which causes the total pressure drop in the turbine. So now the next section is what? Compressor turbine matching. Now, so is it? Let me. Yeah, compressor and turbines are connected in a shaft, as we have discussed in our earlier part. Compressor is at the front section, that is in the cold section, and the turbine in the hot section, and they are connected with spools. It can be one spool or it can be multiple spools. Therefore, they are connected by shafts. So, compressor turbine matching is also required in order to ensure appropriate function. So, compressor turbine matching ensures the turbine produces enough power to drive the compressor. You see, turbine delivers power to the compressor and other shaft-driven compressor. So, which is why we are studying that part in order to ensure power balance between the turbine and compressor, in order to prevent shaft overspeed or underspeed, and also to maintain engine efficiency and to avoid mechanical failure or flow instability. So these are reasons why we are studying compressor turbine matching. So, yeah, so this is the compressor and this is the turbine. And both of them are connected with common shaft. Look, this is the shaft. And that shaft is rotating with 2 pi n, that is rad per second, or n in RPM. 2 pi n. N is RPM or revolution per minute. Okay, so this is compressor, turbine, rotating assembly. Actually, we have high pressure compressor, low pressure compressor, low pressure turbine, high pressure turbine, which are connected with different shafts. And their temperature and pressure conditions are directly depicted here in the TS diagram. Okay, so yeah, temperature at 2 is lower temperature. Again, pressure at 2 is also in the lower condition. Pressure at 3 increasing. Pressure at 4 is increasing. And after 4, pressure is decreasing to 5 because of the cooling effect. Okay. ከአንድ ደቂቃ በኋላ አሁንም ሊዘጋ ይችላል። We have left only 1 minute. So I will send you immediately the link and then you have to join the session immediately. But for now, let's proceed with the existing. Okay, so the compressor turbine matching, we relate the compressor power, the power delivered from the compressor, which is related with M naught HT3 minus HT2. Again, efficiency also be represented here with shaft power or the turbine power. ስለዚህ ይሄ ከኢንታልፒ ከኪውሲ ከኪዩቲ ጋር ሪሌት የምናደርግበት ሜቴድ ነው። አት አምቢያንት ቴምፕሬቸር ኮንዲሽን አት ቲ4 ቱ ኤች 4 ቱ ኤች 5 ኮንዲሽን በዛ ሪሌት የምናደርግበት ነው። እነዚህ ነገሮች ብዙ